Good afternoon, everybody. Welcome to my talk. And in this talk, you will learn how to hack like in the movies and how to become rich. Just to make sure, so I'm sure that everybody knows what are industrial control systems, but I just want to make sure that we all have the same understanding. So this is a bunch of computers hooked up together, which control some physical application. And that physical application is typically something useful for mankind, like power generation or water purification. And because of this physical application, this physical component, industrial control systems are also called cyber-physical systems. And in contrast to the traditional IT networks, the interest of the attacker is in the physical world. So the attacker wants to bring process into some state or to make the process performing certain actions. And exactly that fear of the catastrophic consequences of such attacks is that what makes us so much interested in this type of security and urges to secure them. So what I am doing, so what is my research focus? I study complex continuous processes, something like water distribution or refineries, food production. I study competent attacker with a goal in mind, not like script kiddies. I do not research specifically into the vulnerabilities in protocols and control equipment, but I do consider them while studying attacks on the physical processes. And the questions which I study are what exactly the attacker can do to the process, what she needs to do and why, what needs to be programmed in the final payload, and the most important, are traditional cybersecurity or IT security methods are adequate to protect those networks? Probably the best description of the SCADA's hacking was done by Ralph Wagner. The pros don't bother with vulnerabilities. They use features to compromise ICS. Well done, Ralph. That's exactly that. The features is a key word here. Features is something what is application-driven. So, and this is bringing us to an important point about security. Security is not a fundamental science. It's application-driven. And security solutions exist only in the context of the application. By now, we are still trying to secure these networks by setting up the firewalls and hoping that we can create some super fast encryption. And we are not looking into the features of the physical application, so we're probably missing the attacker. And just to highlight this point, the success story with a specific field where the security science was understood is in e-commerce. After the internet was secured, the attackers moved into the browser, security controls also moved into the browser, and web application designers came up with new design decisions. Security also dictates relevant security properties. So in the context of distributed information in e-commerce, it was clear that CIA is not enough, so the CIA triad was extended to the Parquet and Hexad. And the application where the science of security was not understood. Wireless sensor networks. A big hype for about a decade. Conferences, solutions, promising applications, remaining the promising technology with limited deployment. And the reason for downfall was that the attacker was not well understood. Also, the security requirements were not well understood. There were also unrealistic assumptions about physics of the sensing. For example, it was always assumed that sensing area is a perfect circle and that the sensor nodes can always communicate bidirectionally, which almost is never the case. So if we want to do better with protecting industrial control system, we probably have to start understanding the application. What do I mean? So the vulnerabilities in control equipment are found every day, sometimes in the packs of 1500s. So thanks God, we have ICS CERT who collect those vulnerabilities, and they actually issue the advisories. So I've just picked the random advisory, and they describe the impact like, okay, the attacker can obtain the administrative role on the network. And then the process operators, they suggested, well, guys, now it's your turn to figure out what exactly does it mean to you. Well, that's not like an actionable advisory. To be able to answer this question, it is important to understand, it is necessary to understand what the attacker can do with that specific vulnerability. Are there any further necessary conditions required without which the vulnerability is not exploitable? And how severe the potential impact if this vulnerability is exploited? And to answer these questions, it requires understanding how the attacker interacts with control system and with the process. And this is the biggest mystery of the 21st century. But you will learn it in this talk. This problem was also highlighted in the recent report on the business impact of the implications of the attacks on the US power grid in the attempt to develop cybersecurity policies. So it was stated that the majority of the attack on the operational technology in the last 20 centuries were not made public. So we don't know what is happening there. And the problem then with figuring out the security policies is that you don't have enough data for probabilistic modeling. Well, that's of course a hindrance, but it does not mean that we have to lean on our chairs and wait another 120 years until we collect enough evidence for probabilistic modeling with sufficient accuracy. We can, and we actually should conduct research on our own. Those cyber physical attacks can be studied and understood. So I'll give you an example. Earlier this year, me and Jason Larson, who was giving a talk earlier today, we gave a talk in which we showed that, for example, that's our research, that the control system can be manipulated at will, even if the control traffic is authenticated, signed, and even if it is encrypted. And the attacker can actually spoof process data to hide the impact of the attacks. And that can be also done despite all traditional IT security put in place. So process control and physical applications were also not designed with security in mind. And there are a lot of hanging fruits which we can still discover. So before I jump into the SCADA hacking, I will give a quick introduction about what you need. I will give you the basic of what you need to know about process control so that you could follow the rest. If you know the basics, take photos of me and post on the Twitter. So process control is easier. The easiest way to explain it is in the household heating system. So of course you can always run downstairs and adjust the fuel valve into the furnace yourself, but in the epoch of Raspberries, we automate things. So in this case, it is done with a thermostat. And it's all start with a set point. You first decide, okay, how warm you want your temperature to be. And then the temperature is maintained with the help of control loop. So what is happening? There is a sensors in the thermostat which measures the temperature. The control logics calculate the difference between the is temperature and desired temperature and issues a control command to the valve, like to add some heat or to remove some heat, decrease the heat. So this is the same control loop, just a little bit expanded. And if you see the blue circle, this is where the error is computed between is and required temperature. And we have several terms here, like process variable, which is measured temperature, and controller output, which is a control command to the actuator. Understanding control loop is a must for cyber physical hacking. There is no way you can do it without understanding control loops. In a large-scale operations, it takes a little bit more than a thermostat to control all the logic. And in most cases, it is a programmable logic controller, which is still operates on the control loop structure. So the PLC takes the inputs from the sensor, run the logic, and produce the control command to the actuators. So what is control logic? As the title suggests, it defines the logic of the operations. What should happen or not happen, when, and under which conditions. Control logic does not compute the control commands. The control algorithm does. The most popular and widely used control algorithm on the planet Earth is PID control, which consists of 3 components. So the control command is computed based on 3 components, although in real world, like all 3 components are not widely used. The most widely used is PI controllers. And this is because the derivative component, like if the sensor signal is noisy, the derivative component just only increases the noise. So it's difficult to account for that. So configuration, like the tuning of this PID controllers has a huge impact on the attacker success and requires understanding from the attacker. So the wires from the sensors runs into the cabinet and attached to the PLC, and typically the sensor peaks like 4 to 20 milliamps, and then all these analog signals from the measured signals are then typically scaled to meaningful data in the PLC. Well, even the PLC is not enough to control the complex process. So the PLCs do not have the complete picture of the plant, and they don't have the time trends. So therefore, the process is additionally on top is supervised by a human operator, which monitor that process around the clock. As Jason Larson has told once, that the plant is typically started in a state of imminent failure, and it remains that way. So actually the job of the operator is not to watch the process, but to resolve the alarm, which always flashes. So things goes in the plant, goes wrong all the time, and makes these flashing alarms on his screen. So this is, he has a very nervous job. So now you know everything what you need to know about control system, about like the magic behind the control systems. We are ready to start. So the number one question would be like, why do we want to hack SCADA systems? Well, the cyber criminals are there where the money are. An industry means big business means a lot of money. So sounds like a good place where to be for the attackers. And here I have a quote for you of Alan Parler from 2008. In the past 2 years, hackers have successfully penetrated and extorted multiple utility companies that use SCADA systems. Oh wow, so that has been already happening on the large scale in 2006. We are now in 2015, and we still know almost nothing about how the attackers are doing that. So again, this is why I'm giving this talk. And you've seen that extortion is one of the most prevailing attacks. So in this talk, I'm considering the following scenario. The attacker wants to cause persistent economic damage. And the key word here is persistent. It means we want to cause this economic damage for some time, extended time. And to do so, we have to make sure that the attack, that they do not discover it, so that the inefficiency of the plant will not be attributed to a cyber attack. And I will show you how it is done. So this attack scenario would be useful for extortion, or maybe if you want to kick out the competitor out of the business. All right, so here is a target plant. What is the plan? Go hack it. The typical understanding of SCADA hacking is that once you hack in, there will be some magic red button which you hit, and things are happening in the way which you need it to happen. Well, it does not exist. And actually, to start with, the attacker has to understand what exactly does he want to do to the plant. How is he going to cause that economic damage? So the attacks on the SCADA system could be divided into 3 groups. You can damage the equipment, basically to destroy it or to distract it. You can also go into the production, so to make product unusable, to make producing less product, or to make it production is more expensive. Those 2 groups of attacks will never make the headlines because they must not be reported, and in most cases they are not reported and kept silent. In contrast, if the attacker would like to damage the reputation of the company, then he would make the industrial side non-compliant. So most of the industry are heavily regulations. regulated. So, and the advantage is that those regulations are easily available to the attacker, so he knows what he needs to do. So the most damaging would be attack on the occupational and environmental safety, because that would be result in the lethal accidents or a serious environmental damage. The less damaging attack is environmental pollution, so like when you exceed the volume or some concentration in the emissions, water, soil contaminations, and also contractual agreement, because mostly you have to deliver some product in some time. So when the attacker has to decide, okay, well, right, I know what to do, so how do I decide what is the best for me? Well, this is how the logic flows. Oops, yeah, this is what I, for example, yeah, this was like relative prices for a paracetamol, and you can see if you make just product a little bit less pure, it is very expensive. So this is a consideration. So equipment damage is what comes to that mind, to attacker mind first. The problem with it, it is irreversible. So for example, it's not really usable for the extortion because you cannot undo it. The problem with it also with equipment breakage that it is the collateral damage is unclear. So if something will burst next to the human and kill it, this attack will transit into the compliance violation. The advantage of the compliance violation attack is that, okay, well, you know all the limits, so it's public, you just need to exceed it, you don't need to figure it out. Again, the problem is that collateral damage is unclear because, for example, water contamination can result in like death of fish. Such attacks must be reported to the authorities. That probably, it might be that what you want to do because you want to like damage the reputation, but if you're unsure how well you are hiding your attack, you might not want to do that because the serious guys will be investigating the case. So out of this consideration, it seems like actually production damage is probably one of the best cases because it does not hurt anybody, it must not be reported, so it's a safe area. All right, so now we decided that we go under the production, so we need some kind of find some plan to start studying how do we hack those plans, and also you need a plan to actually test your malicious payload. It is really totally possible to buy a plant. The problem with them that they're extremely expensive. You require a small army of personnel to run it. It is difficult to relocate them. They need a lot of space to be put somewhere. And also if you break a plant, you will then need a lot of new money to fix it. So like experimenting with attacks on the live plants is actually not a sustainable approach. So, and actually in research and development, which is related to any process control, science is never done, like hardly ever done on the live processes. It's done on the models. For this specific work, I used a model, a realistic model of vinyl acetate plant. Vinyl acetate is a commodity chemical which is a building block for most other chemicals like paints, adhesives, and plastics and so on. Yes, and in this talk I will show you, just in a few moments, the complete attack from start to end, how we hack this plant to cause persistent economic damage. There is a saying that behind a great woman there is a great man. The ratio between men and women in security area, and especially in industrial security area, is wonderful for women. So I actually could have as many men as I wanted. So although I was the main brain in this project and I've designed everything, all of those wonderful people were always supporting me and helped me with anything what I needed. So that is a thankful note for them. And okay, so we are now fully ready to start. And so when I decided, like I've been looking at that vinyl acetate plant for a long time, and I've been studying it, and I had interest in it, but I actually did not know even how to start with. And then at one point I decided, no, I really, really want to hack it, but I did not know even what to start with. I've been roaming, I've been thinking, and hoping that it will I will have this idea, and it did not pop up. So, but at some point I remember that in a very I'll come to that slide. In one of the earlier presentations of Jason Larson, he was mentioning the stages of SCADA attacks. On his slide, he thought like, well, the attacker has to go through the stages, and eventually, if he will complete them all, he will probably be able to achieve his goal. So, and what I actually wanted to say here is that like SCADA hacking or cyber physical hacking is similar to IT hacking. Like, basically, you need to design a payload with instructions which will bring the process into the state that you need. It's similar how you encode the instructions into the shell code when you weaponize, for example, buffer overflow. So back to the stages. Well, I don't know for sure whether he ever used them, but he seemed to be very happy that we helped him to formalize them. We now know what you need to do at which stage and why. So this like exploitation never happened in this like perfect sequence, because the knowledge at each stage is never, like the attacker is never, perfect knowledge for each stage is never achieved. Therefore, the attacker circles between the stages and probably have to repeat certain stages like recursively. So I will now take you through those stages which will bring us eventually to the final attack result. So the first stage is obvious access. You need to get into your plant. And this is a stage that is very well understood to the IT attackers. So typically the control network and enterprise network are segregated. You first, for example, go into the enterprise network, and then you use any ingress connection to the control network, and basically you are done. There is no security, do what you want. If you need to invade any specific SCADA devices and you don't know how to do it, no problems. For little money, you can buy yourself a SCADA exploitation kit. Done. If you're like young or modern attacker and you like modern technologies, you can use another approach, which was done by Erin Leverett. So you go to ICS CERT, select a remotely exploitable vulnerability of your choice, scan the internet to locate vulnerable devices, exploit, done. If you're in a modern plant, it might be the case that the analog sensors are already not analog and they actually speak IP and they have like computational smartness embedded into them. So you may want to put your malicious payload or rootkit onto the sensor. No problem. Check the presentation of Jason Larson from Black Hat last year, and he was explaining how to insert rootkit into the sensor's firmware. Done. So this stage is very well understood by most of us. And the problem is that this is the last stage where your IT knowledge is useful. From now on, it will not be beneficial to you. You have to start thinking as a process engineer, as a control engineer, as a chemical engineer. And to start with, you need to understand, okay, well, I am now in this plant. So what is this? Like, you need to understand how it is built and what it is doing. So the first stage after you're in is discovery. You need to figure out and how the plant is producing. Even if you know that you are in the vinyl acetate plant, the exact chemistry and kinetics are actually unique and proprietary to that plant. Then you need to know how the plant is controlled, basically where the location of the control valves, how the tuning of the control loops, control configuration, control algorithms, and so on. You need to know how the plant is built and wired. And the most important, you need to know what are the physical constraints of the plant. This stage of the attack starts a long time in advance with espionage and also reconnaissance activities. In most cases, you will probably the attacker will need to go to the also third parties because most of the, like for example, kinetics and mechanics of the equipment, they are typically done by the third parties. So. Actually, and we've heard about, so this part of the SCADA exploitation is very well understood by the hackers, and actually espionage attacks on industrial facilities started long time ago with certain malware samples dated to 2003. And I will just quote one of the description of one of such espionage attack. The goal of the attackers appeared to be to collect intellectual property such as design documents, formulas, and manufacturing processes. So the attack is looking something like chemistry, piping and instrumentation diagrams, instrumentation list, wiring diagrams. And while you will be grabbing and then studying this documentation, you really need to be able to read it. Do you know what stripper is? It's not Magic Mike. It's a stripping column. So you really need to speak that language. So, all right. We kind of, after studying all of that, we know already, we understand the plan, and we can start making initial decisions, how can we going to achieve our goal? So we want to cause economic damage which hurts. So the easiest way is to destroy the pipe which carries the final product into the vessels. Well, it's the easiest attack, but it's also very obvious, so it will be noticed quickly, can be fixed quickly. So it's not persistent or persistent. The rest of the plan can be quickly divided into two parts. It's reactions and refinement. So the refinement section is actually huge and large. It's like maybe a kilometer long. The problem, so the attacker has lots of opportunity to mess up with the refinement, but also the operators has a lot of opportunities to notice the attacker and to take corrective actions, or maybe even to recycle it back in the loop. So, well, that is like not a reliable path. In contrast, if you mess up with the reaction process in the reactor, you reliably lower the production. So it sounds like a good plan. Important to understand that even this simple analysis will require the input from expert methods. I did not come up to this myself. So, all right, so we resolve our interest, like our focus, to the reactor section. So the first we start to need to understand, okay, what is the equipment there, how it is built and wired and everything. And one of the most difficult parts is mapping the points and the equipment. So this is very time-consuming part, difficult to figure out. So most of the process industries operate on the point abstraction layer. So everything what can be sensed or like sensors, like measured, so sensors and set, so actuators, is a point. So the attacker need to figure out the relationship between tags in the PLC's actual equipment and what it is on the diagrams. And last year we've discovered, last year it was 2012, I am not sure when the Havex was distracted, but that was the first malware caught in wild which been trying already to figure out what equipment is connected to the PLCs. So the attackers, the real attackers are at least this far. They do understand that they need to do this. So after we figure out that, we need to reconstruct, after we know that, we need to reconstruct the location of the control loops. And after we know where the location of the control loops, we need to figure out the configuration of control loops. And the best place to do that is, for example, something what is like instrumentation applications and so on. So this is like one of the applications called Aveva or something. I grabbed it from the internet. So we see here, this is a pressure transmitter, control loop services reactor. Then we see a tag number. Then we see that it is Yokogawa. We have a model number. We have calibration and calibration parameters. And we have the process constraints, like what is the minimum, maximum, what is the operational safe limits. And what is more also important, we have here the username of the guys who has privileges to configure this transmitter. So then we now know which credentials we need to obtain. So we now know, so in that way we also figure out the configuration of control loops. Then we still need to figure out the flows. The things in the chemical processes do not flow perfectly from right to left. And for example, in this case of the vinyl acetate plant, the acetic acid from the tank flows into the reaction section and into the refinement section, into the absorber. So for us, it's a bad news because we wanted just to be busy with the reactor section, but if we will need to adjust that valve, like do something with acetic acid, they will have immediate impact on the refinement section, so we have to watch it out, so it's a bit more complexity. So this information can be obtained from the flow diagrams. Okay, so if you want, we now know a lot about the process, and all we need to figure out is where our controls, because to change the things in the physical world, we need to find the controls. Here's our controls in the reactor section, and this is what probably difficult to understand to the IT people, that obtaining control to something, like control over something, is not meaning being in control of something. First of all, the obtained control might not be useful to the attacker goals. Secondly, the attacker might not be able to issue meaningful commands to that equipment. Today, the guys presented their talk on how the attackers interacted with pumps, and so the attackers has to figure out which language that pump talks, and what is the format of the command, and what should I tell to the pump to do something useful. So, and last but not least, it might be the case that the attacker might not necessarily be able to control obtained controls. What exactly does it mean? With that, we transition to the control stage. So, discovery stage is about static discovery of the process. But physical process has a continuous physical dynamics, and it means that if you adjust something in the physical process, it will have lots of different impacts. And this is what we discover in the control stage. So once the equipment is hooked up together, it started to be related to each other by the physics of the process, even if that equipment does not talk to each other electronically. So if you adjust a valve, everything else adjusts as well. So if you change the temperature, the flow and the pressure also changes. That effects propagate downstream and cause different effects. So the attacker needs to take care about all of those downstream effects. And the goal of this stage is to understand how much we can change, what we can change and how much before we release alarms or everything shuts down. So to illustrate that, this is specific responses of the vinyl acetate plant. So the plot in the red, this is what I've just adjusted. Let me check it. It's heater exit temperature. So I've changed it. I've just adjusted that valve for some time. As you can see, everything has changed, and the response has different shapes, different time scales. And what is more interesting, you see this is two control loops, and in one case something goes down, and in another case something goes up. So those responses are not logical and are not easy understood. So there's no way you can just know what is going to happen. And one of the reasons for that is that there are millions of parameters which influence the responses of the process to the manipulations. So this is the control loops which you've seen on one of the previous slides. So, for example, in my previous works, when I was working on some exploits to exploit some specific features, I've been extensively studied these parameters, and I really have to take care of these parameters while writing my exploit. The second reason of those strange behaviors of the processes is process nonlinearity. What does it mean? The problem is that, in short, it means that the response of the process is not proportional to the applied input. So, for example, how the process behaves when being heated from 140 degrees to 150 degrees is completely different when the process is further heated to 160 degrees. And the behavior of the physical processes to the controller, not only to the controller, to the humans, to us, is only known to the extent of the modeling. We only understand process behaviors, those which we already modeled. And the same to the controller. The controller cannot model processes beyond its controller model. So if the control algorithm has never been tested to perform at 160 degrees, it might be well that the process will go uncontrollable. So if you see on this input, I've just randomly adjusted some valve, and this is a reaction of the sensor. As you can see, the temperature change is clearly nonlinear, and you see these overshoots which are extremely dangerous because they actually cause alarms, which we don't want to cause. So, like, for example, if you can see here, another problem which the attacker will need to deal with. For example, in this specific plant, there are a lot of control loops which has ringing effect. So even if I change something, if we even change something slightly, and just if you see this red circle, the deviation of the ringing is actually quite small. The problem is that it causes this effect propagates, and in other control loops, it causes ringing in the ratio of 1 to 150. And the problem was that those peaks were causing alarms. And it was a big problem because it meant that we were not effective in controlling a lot of control loops. And we had to find the way how we still could do it and overcome this problem, which could be done like in another presentation. So all of these issues the attacker has to deal with. And basically, in many cases, the process really became uncontrollable and unusable. So we tested actually two types of attacks. The step attack, when you bring the process in some state and leave it there, and also periodic attacks. So you attack it, you let process to recover, you launch another attack, you let process to recover, and so on. So, and then to keep it probably short, so the outcome of the control stage was to understand how each control loops behave under different attack parameters. And that was a lot of knowledge. And obviously, so since it was our first work, we definitely probably, we still even did not know how it works. So we could not automate it. It is now actually work in progress. Because now we kind of know what kind of information we need to figure out. In any case, the outcome of the control stage is attacker's understanding which control loops he can control and to which extent. So this XMV, it stays for the manipulated variables. It's basically control loops. So number 157, it's a number of control loop. So the attacker categorized control loops based on some certain useful parameters to him. And in our case, it was sensitivity to manipulations. And we want to select, understand which controls are reliable for us. And then we also have to figure out the propagation of alarms, because if you want to persist, we don't want to cause any alarms. So we have to figure out the attack parameters which causes alarms, because we did not need to trigger them. So basically the marginal attack parameters. Okay, so we now have the attack plan. We now know how we can control the plant. We can actually start designing the specific damage scenario. So this is a stage of the attack which is least understood by the traditional IT hackers. How do we break things? In most cases, coming up with some meaningful, working attack scenario requires the input requires input from the expert subject matters. And accident data is actually a good starting point. So if things went wrong in the past in some way, so there is a good chance that they will go wrong in the same way again. So you can go into the governmental agencies' accidents reports or plans own plans accident databases and so on. So you can easily get inspired. The challenge here again, the plant may not be designed in a hacker-friendly way. So there might be no sensors which need to measure specific parameters of our interest. The information about the process may be spread over multiple sections of the process, making attacker invading more devices. And control loops might not be designed to control different parameters which the attacker needs to control. So the attacker have to figure out all about that. So since we want to reduce the production of vinyl acetate, we need to figure out how to measure the concentration of vinyl acetate molecules in the reactor exit. The concentration of the chemicals is typically measured by the analyzers. In the vinyl acetate plant, there are 4 analyzers and none of them in the reactor exit. The only 2 measurements which are available to us is the flow and the temperature. That is was not helpful because we all know if you can't measure it, you can't manage it. How we are going to compare the effect of the attack? So we've been, and I'll go back to the slide. We could measure the effect of the attack at the decanter, at the end of the plant. But measuring there is too late for us because that effect is available to us in 6 or 8 hours. So that's not sustainable. So we've looked here and there, and it seems like, no, we cannot measure the impact of our attack. And so, I was again looking for a solution, what do we do? And then I remembered another presentation of Jason Larson. So basically, there are two answers. Everything can be measured in two terms. There is a technician answer, which tells you something increasing or decreasing. And there is engineering answer, which tells you that, okay, by how much? And so basically, in technician, we could obtain the technician answer with a proxy sensor, which is actually reactor exit temperature. So if reactor exit temperature is decreasing, it means that less reaction is happening in the reactor. It means that our attack is successful. Well, it's already a good sign, but it is still, this accuracy is not enough for us to compare the effectiveness of different attacks. So we desperately needed the engineering answer. So, and then I had this idea. So, in fact, the control logic is actually very complex. There are a lot of optimization applications. So, there are a lot of computations are done on the process before you control, issue those control commands. And so, we wanted to see whether there is in the control logic there is some intermediate computations which might be useful to us. So we knew that, I knew that we have to look for some ugly differential equations. And it seems like we found the place where those numbers are computed, but the problem was that those very strange numbers. We have a gut feeling that this is a useful number, the right place, but the numbers did not tell us anything. We've been trying all possible math to make sense out of them. We were not successful. Eventually, with persistent, after 2 weeks, we were able to make sense out of them. And we finally could compute the concentration of vinyl acetate. And once we had that, we can actually monitorize the effect of our attacks in dollars. So that was a huge success to us. So the outcome of the damage stage is a portfolio of attacks which the attacker can play at the opportune time. Okay, so we now know how to damage the process. We are still not done. We want to persist. It means that we want to avoid attribution. How do we do it? In the IT world, it's easy. In physical world, if you change something, the effects are there. So you can't simply lie and say, oh, no, it's not happening. So the meaning of the cleanup stage is misdirect the avoid making the operators believing that something else is happening to the process and not a cyber attacks. So, and actually, this is just informative slide that having the operator in the control loops is actually what turns cyber physical systems and socio-technical systems. And to hack this kind of socio-technical systems, so to fool the operator, the attacker need to understand the vulnerabilities in his job, in his in his decision-making process or procedures he needs to follow. So if plant since we are not raising alarms, they will not notice attacks immediately, but if after some time the plant will become unprofitable, they will start being concerned and they will try to investigate. So if the attacks, for example, it's just one of the scenarios, but we figured out more scenarios. So if the attack is attributed to, for example, is time to a particular employee shift or maintenance work, then the employee will be investigated rather than the process or like applications. So, for example, just pick several ways how the temperature can be in the reactor can be increased. Wait for the scheduled instrumentation calibration. Perform first attack. Wait the maintenance guy being screamed and yelled at. Play the next attack and repeat. That will drive them crazy. So this is an example. This is 4 different attacks. So this is 4 different attacks from the damage stage, which caused variation in the temperature and the reactor temperature of different amplitudes. So if they will get tired and they will start, the reactor will be deemed malfunctioning, the plant owners, they will invite a specific forensics team to investigate. So the attacker needs to understand the metrics. So nobody can look into the reactor. Typically, the reactor is tested by the specific metrics, which is calculated based on the inputs and outputs parameters. So the attacker needs to understand the metrics which they use and just like change the attack patterns according to the debugging efforts of the personnel. So this is how, like a little bit a larger state of how it looks like. So you have to perform there are a lot of tasks the attacker has to do until he comes to the final payload. And if you understand what the attacker needs to do and how, there is many ways how we can exploitation harder or look for the attacker where he goes. Post-Istanbul. It seems like the offenses are basically all of those plant modernization and pervasive connection of the plants to the internet is actually pave the path for the attacker into the plants. We know that they're inside, and it seems like offenses are 20 years ahead of defenses. Nevertheless, and the problem is also that we did not see much going on in the defensive side. It seems like defense is paralyzed. But the point was like, again, so why do we do this research? Because this, yes, we do not have much of evidence of how the attacks are happening, but again, it can be studied. So the takeaway of this talk is that, first of all, the SCADA hacking can be more sophisticated than simply blowing, breaking, and crashing. There could be more subtle possibilities for the attacker. And do not neglect the espionage attacks. They hurt later because the attackers are not collecting information for the national libraries. Better understanding what the attackers need to do and how is actually will allow us to eliminate low-hanging fruits and make exploitation harder. And if we understand what the attacker is doing, we can actually look for the attacker. So we can wait for the attacker where he has to go because certain credentials has to be obtained, certain information need to be collected. And in most cases, process control stage, this dynamic discovery of the process, must be done on the live process. So you can also have anomaly, you can look for the attacker at the process level. That was the end of my talk. Thank you very much.